Hello, and welcome back to More on Maths. In today's video, we're going to be exploring how you can approximate a log without a calculator. I got a YouTube comment recently on a video where I was finding a solution to an equation, and the x was left in the form of log base 5 to the 3. The commenter was wondering, how could you then find what log base 5 3 is as a decimal without a calculator? And that caused me to do a bit of research, and it turns out you can approximate a log to as many decimal places as long as you've got the time, using Simpson's rule, which approximates integrals, so long as you've converted the logarithm you've got into a natural log and then into its equivalent integral. That's a brief explanation of what we're going to do here, but let's get right into it now. Log base 5 of 3 can be written as a fraction if we use the log law. Log a b is equal to log c b over log ca. C could be any number, it could be base 10, it could be e, 4, 5, 6, it really could be anything. But in this case we want to convert it to a natural log, which is a log with base e. So we have log e of 3 over log e of 5. And that's the same as ln 3 over ln 5 if we simplify it. So now's the part where we split off and we approximate our ln 3 and ln 5 separately. Ln 3 is actually equivalent to 3 to 1 of the integral of a function 1 over x dx. And that's a key step which helps us to do this, because we can actually approximate integrals without using a calculator. We have a few numerical methods: Euler's, improved Euler's, Simpson's, and the mid-ordinate rule. We're going to be using Simpson's today, which is covered in the A-level further maths syllabus. So you wouldn't be expected to use this in an A-level maths exam, and you wouldn't be expected to do this at anything without a calculator in the A-level maths exam. But this is kind of a fun little trick you can kind of explore. It's nice to know how people do approximate things like this and do find the value of things like this. Simpson's rule. For any integral of b to a, it can be approximated as h over 3 of a sum of a first y value of a strip plus the end y value, two lots of all the even y values, plus four lots of all the odd y values. So we've got a few things we might not have seen before. We've got h and we've got our y's. But let's start with h. You should know that integration is finding the area under any curve by splitting it into strips. Here we've split the area under the curve into 1, 2, 3, 4, 5, 6 pieces, and we've got 7 ordinates, which is what we're referring to when we're saying y0, y1. H is referring to the width of these strips, and we can work that out by taking our b and a and dividing it by the number of strips we want. Today we'll be using 4, but the more strips you use, the more accurate of an approximation you'll get, which means you can get it to more significant figures and closer to its true value. This 3 take 1 over 4 means h is equal to a half. A table is really useful for this next bit, as we're dealing with a lot of x zeros and y zeros. First of all, we've got our xn column. As I mentioned earlier, we had 6 strips in that diagram, which meant we have 7 ordinates enclosing them. So now that we've got 4 strips, we're going to have 5 ordinates, which means 5 x values. Our first x value is going to be 1, as that's where we're starting from. And then we're going to add the width of our strip to this one to get our new strip. 1 plus a half is 3/2. We're going to continue adding our h on to the previous x to get our next one. So we get 2, 5/2, and 3. Our next column is the y column. To get these y values, all we have to do is substitute our x values into the 1/x equation, which is actually the same as getting this reciprocal of a fraction. So we get 1, 2/3, half, 2/5, and a third. Our next column is the multiple column, where we have to multiply the first strip by 1, as well as the last strip, our even strips by 2, and our odd strips by 4. Then we combine our multiple with our y values. We get 1, 8/3, another 1, 8/5, and a third. Finally, we need the total of these, so let's add our fractions first. 8/3 plus 1/3 gets us 9/3. Add that to our 8/5. 3 can also be written as 15/5. So we get 23/5. We add our 2 1s. 10/5 plus 23/5 is 33/5. So that's our sum of all the y values. Then we just need to times it by h/3. H was a half, which means we're actually timesing it by 6. So we get 33/30, or 11/10. That's our approximation for ln 3. I'm going to leave it as a fraction for now, because it will help that when we're dividing the fractions later. We don't need to keep dealing with loads of decimals. But let's do the same for ln 5 now. Ln 5 can be written as 5/1 of 1/x dx. We'll approximate it with 4 strips again. So this time our h is 5/1/4. So it's 1. Let's draw a table. Okay, so for our x column, we're doing the same number of strips, so we have the same number of ordinates. We're starting from 1 again, but we're just adding h each time. We're just adding 1 this time. For our y column, we're doing the reciprocals again. 1, a half, a third, a quarter, and a fifth. The multiples are the same as last time. Times 1 for the ends, 4 for the odds, and 2 for the evens. Then we do our multiple times the y. We get 1, 2, 2/3, another 1, and a fifth. Now we can add them up. Let's do our fractions again first. 2/3 we can write as 10/15 plus a fifth, which is equivalent to 3/15. So that's 13/15 there. Let's add our 1, 2, and 1. Add them together then. We have 4 and 13/15. That's an improper fraction. That's 4 times 15, which is 60, plus our 13, so 73/15. Times by h/3, which was 1/3. we're dividing 73 over 15 by another 3 to get 73 over 45. That's our approximation for ln 5. We're getting to the more exciting bit now, when we're putting our ln 3 and ln 5 back together. Ln 3 over ln 5 is equal to 11 over 10 divided by the 73 over 45. So 11 over 10 times 45 over 73. 45 times 11 is 495 over 730. So we've got a common multiple on the numerator and the denominator of 5. 495 is just one lot of 5 away from 500, which would be 100 times 5. So that's 99 on the numerator. 730 divided by 5 is 146. This means this is our fractional approximation for log base 5 of 3. But let's do it as a decimal. So we'll use our classic bus stop method, division, to get our final decimal. I don't know my 146 times table, so I'll write what I do know down here. Might need a few more than those. We'll use that for now. 146 into 9 goes 0 times, into 99 goes 0 times, but into 990 it's not going to go in more than 6 times, with a remainder of 114. We do need a few more of our times tables. It's going to be a couple more than the 6. So let's try the 8. $1,168. That's too big. So let's subtract 146 from that. Get 1,022, which will fit, which means it goes in 7 times, with a remainder of 118. Now our 8 will fit in, with a remainder of 12. That goes in 0 times, so we've got a remainder of 120. We could keep going, although because we've only done 4 strips, I don't think our approximation is going to be more than a couple of decimal places. So I'm going to say that our approximation for log base 5 of 3 is 0.68 to 2 significant figures, or 2 decimal places. I'll check it on a calculator now. And there we have it, our actual value is 0.682606. That carries on, but you can see we have done it to 2 significant figures, which is pretty impressive. It's a lot of work. You wouldn't want to do that in an exam, but very cool to see what goes on behind, how people have found these in the past. Because at one point, people may have used Simpson's rule before they had calculators, where they could just stick it in and get a value. But there we go. Maybe one day we could try it with more strips. I'm currently working on 6 strips, which deals with a lot more decimals and fractions. But maybe we could do that if we receive, let's say, 25 likes on the video. If people would be interested, we can see how many decimal places we can get to with 6 strips, and then maybe we go further. But I hope you found this useful. You learned something new. It's not something that would be covered in the A-level curriculum, or even the further maths A-level curriculum. But yeah, something quite fun. Feel free to check out the rest of the Moral Maths channel, where we'll be posting more videos like this in the future. If you like the video, please consider subscribing or suggest other explanations which I can walk through in the future. Thank you for watching.